So welcome to our video on why confocal microscopy is challenging, and of course, I won on bioimage analysis. So confocal microscopy can be challenging. Let's bear in mind the principles behind it. So you have fluorescence microscopy where um, thick 3D objects can be out of focus and difficult to optimize the approach by which we get the right light wavelengths coming back towards us. And the issue is there that the light from all the planes hits the image plane. And if we look at an example on the right, we can see that for fluorescence microscopy, the red and blue lines, image parts, hit the image plane at different parts than the center, whereas we see the green part in the middle best. For fluorescence microscopy, we remove these parts that hit the image plane at the incorrect part by having a pinhole here. That means that the light refracts, light enters only at the green part, and that's refracted back to the image plane at a slightly later point, and that's the difference for confocal versus fluorescence microscopy. So this eliminates the out of focus light. However, what we have to consider is that therefore estimating the intensity of fluorescence between different experiments or even within experiments is challenging. So we have to bear in mind that the resolution has its limits as a finite resolution, and therefore very, very small structures that are smaller than the Eil's diffraction limit are difficult to resolve. We may find there's optical aberrations, distortions, inaccuracies, this kind of warping effect that you might get with certain images when this is what you're trying to image. The signal to noise ratio will vary as well. So poor resolution samples with a low dark images essentially, and high background noise will be difficult to resolve. Photo bleaching and also phototoxicity are also issues. Prolonged exposure to excitation light can mean that we get the loss of fluorescence known as photo bleaching, or we get cell damage known as phototoxicity. An example of this is the optimal buffer, which in this case was a Scorpius Ringer's buffer, which showed less of both. So we see here on top images where we have the normal buffer where we get kind of this photo bleaching and phototoxicity over time, whereas on the bottom we get a better buffer which shows more consistency over time. You can see that graphically the relative fluorescence is the same for the lower panel, whereas for the upper panel it declines over time. And this might be to give false positive inferences. We also need to consider the fluorophore variability and bleed through as well. So things like their emission spectra or quantum yield may give inconsistency in signal intensity measurements. We also may get kind of spectral bleed through between different fluorophores, which affects the multi-channel images. Samples vary. We know that, and therefore comparing between different experiments is a challenging process. We may apply different approaches of segmentation, so essentially go from these images to kind of binary or simplistic images where you have light in the background to identify the volumes and shapes that are present. But this isn't easy, especially if they're so close together or blurred and so on. We also have to consider the subjectivity there. So we're manually optimizing the threshold. We're defining regions of interest that depend on the data and the user as well. So that's why confocal microscopy is non-trivial, and therefore we have to approach it with due care.